Hey folks, welcome to part three. We're going to be now talking about uh, stoichiometry and using balanced chemical equations to do some calculations. All right, so stoichiometry is the name of this, and I've hinted at this already a little bit. This is going to be using balanced chemical equations to calculate, say, the maximum number of product formed from a given amount of reactant, or even the maximum mass of product given mass of reactant. Okay, so the first one is what we call mole to mole stoichiometry calculations. So this is all about coefficients. So the coefficients provide the molar ratio between any two substances in a chemical equation. Here's another one. We haven't seen this one quite yet, but this is ethanol with oxygen, right? And so we see that 1 mole of ethanol would react with 3 moles of oxygen to form 2 moles of carbon dioxide and 3 moles of water. So we can uh, write these as mole ratios, which are also conversion factors. So let's say the question is, how many moles of oxygen are needed to react with 5 moles of ethanol, right? And so it's a 1 to 3 ratio based on the balanced equation. But we don't have 1 or 3, we have 5 moles of ethanol. So if we put a 5 here, what needs to go here? That's the question, right? So we can look at the mole ratios. 1 mole of ethanol to 3 moles of oxygen, or 3 moles of oxygen to 1 mole of ethanol, um, depending on the question, right? Just like we always know, if you have a conversion factor, you can always write it either way by flipping it. So then we have moles of ethanol. So like that's kind of our measured quantity. We want moles of oxygen. So we use a conversion factor with moles of oxygen on top. Take, sorry, I didn't flip through the animations here. So we already have it crossed off, but 5 moles of ethanol times 1 mole of oxygen per mole of ethanol. And we can see that moles of ethanol cancels out and we're left with moles of oxygen. And we get 15, right? Which is that 1 to 3 ratio that we expect. Okay, that's an example of how we would use stoichiometry and mole to mole stoichiometry. Here's practice exercise 523. A balanced chemical equation is given. If it's not given, you have to balance it, but it is balanced here. What is the maximum number of moles of CO2 produced from 6 moles of glucose? So you might be able to just look at this and see what we have here. But if we want to do this in a strategic, systematic way, we can find our mole ratios, right? So one mole of C6H12O6 over 6 moles of CO2, or we could have 6 moles of CO2 over 1 mole of glucose. And we want to find the number of moles produced, so of CO2. So this would be the one we want to use. Now I want to pause actually here and mention again um, that the concept of our units has expanded, right? Because I can't just say 1 mole anymore. I have to say 1 mole of what? Because we're talking about multiple species, multiple molecules. And so I have to be clear, I'm talking about 1 mole of glucose and 6 moles of CO2. And so our units are kind of getting long here, but it's important to keep track of which one or which molecule or which species we're talking about. So once we determined our conversion factor, we can start with our known quantity, which is 6 moles of glucose times the conversion factor that's appropriate that puts carbon dioxide on top. And we see that 36 moles of carbon dioxide would be produced from 6 moles of glucose. All right, I mean, you can go the other way too and say, if you produced this much CO2, how much glucose reacted, right? So it's the same ratio. You just use the other conversion factor and go either way. So we can expand from mole to mass stoichiometries, but the reactants and products do not are not in proportion relative to masses. They're in proportion to the coefficients, which are number of molecules, right? Obviously, the total mass of reactants and total mass of products has to be constant. That's the law of conservation of mass. But we only have molar ratios. We don't have mass ratios. So we have to basically use two parts with the mole in the middle. Okay, so here's a nice diagram. If you're given a mass of, let's just say, substance A, we will use the molar mass, as we did in last section, to find the moles. We're going to use mole ratio from the balanced equation to get moles of B, and then we're going to use molar mass of B to get the mass of B. So it's three-step process here, okay? But it's a consistent 3 steps, okay? Number 1, convert the mass of the given to moles using molar mass. Step 2, convert moles of given to moles of asked for substance using molar ratios, the coefficients from the balanced equation. And then 3, convert moles of asked for substance to mass of asked for substance using molar mass. All right, how about an example here? So sodium azide is in your airbag, and it can undergo a very fast decomposition into sodium solid, and it produces a bunch of gas, nitrogen gas. So that's how your airbag fills up. So what mass of nitrogen is produced when 130 grams of sodium azide decomposes in an airbag according to this balanced equation? So step 1, we need to, well, let's just think about what we're doing here, right? We're going from the mass of sodium azide to the mass of sodium. And so we need to get to moles, right? So we need to convert NaN3 to moles from mass. And let's see. So we look on a periodic table, and we want to find the molar mass. We look up sodium, and it says that sodium is 22.99, and that would be grams per mole, right? That number on the periodic table. Nitrogen is 14.01 grams per mole, and we have 3 nitrogen atoms in this molecule, and so that would give us a total molar mass of 62.05 grams per mole. Now, if I want to convert grams into moles, right, I'm going to start with my known quantity, which is a given of 130 grams sodium azide times, now 65.02 grams per mole can also be written as 1 mole per 65.02 grams. This is sodium azide. Okay, so now I get 2.0 mole sodium azide. So here is all of that again, right? So step 1, we have moles of sodium azide, and now we can look at the mole ratio. For every 2, we get 3 nitrogen. So if I have 2.0 mole sodium azide, I have a mole ratio of 3 moles of N2 for every 2 moles of sodium azide. These numbers work out nicely, right? So we end up with 3 moles of N2. So for every 2 moles, we get 3. We have 2, so we get 3, right? But we can use the mole ratio to do that strictly mathematically. So step 3 now, we want to go from moles of N2 into mass of N2, which is, let's see, so molar mass of N2 would be 14.01 grams per mole for each nitrogen times 2 is 28.02 grams per mole. So if I take moles, which is 3.0 moles of N2, multiply by the molar mass with, right, I want to go from moles to grams. So I put grams on top. Mole cancels out. And we get 84 grams of N2. So if we start with 130 grams of sodium azide, we would get 84 grams of N2. Without having to do all that work over again, how many grams of sodium do we get? This is actually a very simple step once we did all the hard work, right? Because conservation of mass, right? If over here we have 130 grams, then the total here has to still be 130 grams. So how much Na did we get? It'd be 130 minus 84, which would be, let's see, 46 grams, I believe. Okay, so we took these as 3 separate steps, which is perfectly fine to do. But you may see that at each step, we used the answer to the previous step, right? And so we can actually combine all of these into one calculation where we can keep track of the steps. So our unit plan would basically be grams of NaN3 to moles of NaN3 to moles of N2 to grams of N2, right? And each arrow represents a step, right? Or a conversion. There we go. But we can combine it all into one. Everything cancels out until the end we get grams of N2. Okay? So we have balancing chemical equations here. There's kind of a lot in this section. We have the parts of a chemical equation. And then we learn how to balance them by adding coefficients. Once we have balanced chemical equations, we get mole ratios, and we can do stoichiometry, like mole to mole stoichiometry or mass to mass, using moles as the bridge. Okay, so plenty more practice there with that. You can be found on Sapling and in the back of the chapter. All right, that's it for today. Thanks, everybody. See you next time.